Right, good morning, good afternoon, good evening, class. This is Mr. Arocena, and on today's video, we're going to be talking about Bronsted-Lowry acids and bases. So in the first part of this unit, we talked about Arrhenius acid-base theory and what defined an Arrhenius acid and what defined an Arrhenius base. So the Arrhenius acid, oh, that's a terrible color. So the Arrhenius acid, as a quick recap, these created H plus ions, and they could usually be determined by or easily spotted by starting with an H. And the Arrhenius base, they created OH minus ions, and you could easily tell because they had ended their formulas with OH. So Arrhenius acids created hydrogen ions, usually start with an H. Arrhenius bases create hydroxide ions and usually end in an OH. But there were a couple of exceptions which I mentioned in some of the examples we talked about in the last lesson. So today we're going to talk about a more robust definition of acids and bases, and that's the Bronsted-Lowry theory. But before we talk about that, we have to discuss what happens to hydrogen ions when they are dissolved in water. Okay, so this is aqueous hydrogen ions. Right. Now, hydrogen ions, if you think about it, hydrogen ions are really nothing but protons, because if you recall from like Science 9, a hydrogen atom consisted of one proton in the nucleus and then one electron orbiting around it. And if you strip the electron off of it to create a hydrogen ion, all you're left really is a single proton in the nucleus. Now, what this means is that the hydrogen ion or the proton has a really large charge density, so it's very positive for its small size. What this means is that, well, like any other positively charged object, these protons are attracted quite strongly to any area that has a negative charge, and lo and behold, it attracts itself quite easily to the negative end of water. So if you remember from, I think, Chem 11, where we talked about water, so here's oxygen, here's the hydrogens. Okay, because of the way that the bonds are arranged, this part of oxygen is slightly negative. So what happens is that this proton, the proton, or the hydrogen ion, I guess, they're kind of the same, is very much attracted to this part of the water molecule. Okay? And what this means is that the water molecule in the presence of hydrogen ions actually ends up creating a new molecule. Okay? So I'll illustrate that in, again, a little more detail in the next slide here. So here is water. So this is water. This is the hydrogen ion, and the hydrogen ion attracts itself to the negative end of water. So this part is negative. Okay, and what this creates then is a new molecule, which kind of looks like water. It just has an extra hydrogen. This molecule here, if I'm not mistaken, is called hydronium. So hydronium has the formula H3O+. There we go. So it's basically a water molecule with an extra hydrogen, and because it has the extra hydrogen, it has an overall positive charge. Okay? So this is what happens with hydrogen ions when they're in water. They don't actually stay as hydrogen ions because they are very positive. They are very much attracted to that negative end of water. Okay? And then they form this structure here called hydronium. Okay? What does that mean for acids and bases? Well, this will change the definition of what happens to an acid when we dissociate it in water. Okay, so the acid dissociation or dissolving of an acid, in previous classes you would describe it as follows. So take, for example, hydrogen chloride or hydrochloric acid. Hydrochloric acid, when dissolved in water, will create hydrogen ions and chloride ions. So this is what the Arrhenius definition is. So Arrhenius acid creates H+. Okay, or it creates or releases H+. Okay. Now, with a with our knowledge of what happens to this hydrogen ion doesn't actually stay a hydrogen ion. The hydrogen ion ends up combining with water to create this. Okay? So we'll change this equation ever so slightly. It now looks like this. Given the true nature of hydrogen ions, the hydrogen chloride or the hydrochloric acid will combine with water to create hydronium ions. So here's it is combining with water to create hydronium ions, and it's chloride ions. Okay? So this kind of gives us a slightly different definition of an acid. An acid no longer just creates or releases hydrogen ions. An acid will actually act in such a way that it creates this substance here, hydronium. Okay? Although we're not going to use that as our definition of what an acid is. Okay? Instead, we're going to use the fact that the hydrogen chloride gave away this hydrogen ion. So Bronsted and Lowry came up with the following definition, and it's much more general than the Arrhenius theory of acids and bases because it applies to a lot more things. So an acid ends up being any substance that donates a proton, okay? Or in our case, you can think of it as a donating hydrogen ion, okay? So similar to the Arrhenius theory in that it releases the hydrogen ion, but really we should think of it as it's donating it. Okay. Now, if the acid donates a hydrogen ion, then the base must do the opposite. So the Bronsted-Lowry theory is a base is any substance that accepts a proton or accepts a hydrogen ion. Okay. And this is important because if you recall from our previous lesson at the end, we were giving some common household examples. There was one particular base that looked like it shouldn't have been a base because there's no way it could release hydroxide ions because it didn't have any hydroxide ions. However, with this definition of Bronsted-Lowry base, you can see that it actually does fit the Bronsted-Lowry definition of a base. Okay? Now, if you don't remember what that example was from the other lesson, that's okay. It's right here. This is ammonia. Ammonia is a household cleaner, quite on the basic end of the spectrum, and this is a base. Now, why is it a base? Well, let's take a look. Here's what happens to ammonia when it comes into contact with water. It creates an ion called ammonium, and here's the mechanism. Okay, notice here, this is the water. One of the hydrogens from the water gets given to the ammonia to create NH4, and then there's OH minus at the end. Okay, so the ammonia is a base because it is accepts a hydrogen ion from the water, and that's what defines ammonia as a base. Because when you look at the formula for ammonia, there's no way that this ammonia can release hydroxide ions. So we can't use the Arrhenius definition of a base to really define this as a base. But the Bronsted-Lowry definition of a base being a hydrogen ion acceptor, a proton acceptor, works because the ammonia here is accepting a hydrogen from our water molecule. Now, as a result of that, when it accepts the hydrogen ion, the water does get turned into OH minus. So there is hydroxide ions present when ammonia comes into contact with the water. But the ammonia itself does not release the hydroxide ions. The ammonia takes a hydrogen from the water and forces the water to become hydroxide. Okay? So to recap that, the ammonia has accepted a proton from the water and forces the water to become hydroxide. The fact that it accepts a proton is what defines the ammonia as a base. Okay, so ammonia has accepted a proton, so it acts like a base. Now, what about water? Okay, so what about water? So take a moment to think about this before proceeding to the next slide. Okay, now water, I'll rewrite the equation again here. Here's the equation. In this ammonia reaction, what does the water do? Well, the water loses a proton. Although losing might be a bad word in light of what we've done. Let's call it donating. Has donated a proton. Now, because water donates a proton, and according to our Bronsted definition of an acid, water in this case actually acts as a acid because it's donating a proton. So because the water donates the proton, it actually acts as an acid, which is kind of weird because you don't normally think of water as an acid because water is pretty neutral. But in this case, the water is acting as an acid. And again, the reason it's acting like an acid is because it is donating a proton. Okay. Here's another example. This is what happens with acetic acid when it comes into contact with water. Okay. So here's the acetic acid. This substance here is acetic acid. Okay. There's water, and then it creates this. Okay. So take a few moments. If you want to pause the video and think about it, go ahead, and then we'll proceed afterwards. All right. So in this case, the acid is going to be the acetic acid, CH3COOH. You might be thinking, it's like, okay, we talked about this the other day in that this doesn't look like an Arrhenius acid because it doesn't start with an H, and I can't tell which H is going to be given up. However, looking at this formula, it becomes clear that the acetic acid is going to donate this hydrogen to the water. Okay, so it's donating this hydrogen to the water to create the hydronium. Now, water in this case is actually going to act as a base because it is accepting the hydrogen from this acetic acid to become this hydronium ion. Okay, so water, depending on the situation, water can actually act as both an acid. Okay, if the water gives up a hydrogen, it acts as an acid. And if the water accepts a hydrogen, it can equally act as a base. So depending on the situation that you're dealing with, water can be one or the other. Okay, and in some weird cases where we deal with multiple steps of acid-base reactions, water could actually be both, which is interesting. Anyways, here you go. So acids donate hydrogen ions, and bases accept hydrogen ions. And this definition is much more robust than the Arrhenius definition. And you can actually define substances that you wouldn't think as an acid or a base as an acid or a base because they're likely to donate or accept protons or hydrogen ions, I guess, whatever you want to call them. They're effectively the same. Now, some substances have the ability to donate multiple ions, and we call these substances polyprotic acids. Polyprotic bases also exist, I suppose, because there are some substances that can accept multiple protons. So polyprotic acids are basically anything that has a lot of hydrogen ions it can give up. So an example here, this is carbonic acid. Notice the carbonic acid has 2 hydrogens it can give up. Okay. By this slide, we can also say things like monoprotic acids donate 1 proton. Then you can have diprotic acids. These donate 2 protons. And then triprotic acids could donate 3 protons. I'm not sure what the 4-proton donators are called. Either probably tetraprotic would be my guess. Yeah, probably tetraprotic if we're following standard chemistry procedures. But generally, we don't deal with those at this level. So triprotic acids and diprotic acids are kind of common here. But all it really means is that it just has the ability to donate more than 1 proton. Okay, so diprotic donates 2, triprotic donates 3, monoprotic can donate 1. Okay, and it's kind of neat. Now, the really neat substances are what we call amphiprotic substances. Now, these substances have the ability to act as either an acid or a base. So these act as either a Bronsted-Lowry acid or a Bronsted-Lowry base, and it depends entirely on the situation. So a good example is water. Okay. Because water has the ability to gain a hydrogen ion to become H3O+, and water has the ability to give up a hydrogen ion depending on what it's interacting with. Okay. Other examples of amphiprotic substances would look like this. This is dihydrogen phosphate. Okay, and then there's hydrogen sulfide. This is hydrogen bisulfite. No, not bisulfite. I actually don't remember the name of this. This is bicarbonate. This is the bicarbonate ion. I guess it would be a bisulfide ion, I guess, right? So all three of these substances have the ability to either accept an acid, or so not accept an acid, accept a hydrogen, or the ability to donate a hydrogen. Okay. Now, with these three substances, they all share one thing in common outside of having hydrogen ions. Okay. And hopefully you guys noticed it. If not, I'll give you a moment to think about it. Okay. All right. So the thing that these all share in common is they all have a negative charge. Okay. Because remember, when you talked about the beginning, the hydrogen ion needs to be, or is very much attracted to negative charges. So if the substance has a negative charge, there's a high likelihood it can attract hydrogen ions. Okay. Now similarly, they all have at least one hydrogen ion. Okay, because you can't be an acid if you can't donate a hydrogen ion. So they all have at least one hydrogen ion, at least one hydrogen to give. Okay, and at least one negative charge. Okay, so amphiprotic substances have this in common. Okay, so, although oddly enough for water, but then water is kind of polar. Okay, so I guess make a note here. This one negative charge or is polar enough to have a negative end. Similar to water. Okay, so amphiprotic substances are characterized by having at least one hydrogen they can give away, and they have at least one negative charge, or they're polar enough that they have a negative charge. Okay. All right, now let's go through some examples and see if you can identify what the acids and the bases in each reaction. So I believe there are 4 reactions, or maybe 3. Let's put them all up. So here's the first. That's dihydrogen phosphate. The next one is bicarbonate and dihydrogen phosphate, and the last one is ammonia and the sulfide. Okay, so pause the video, take a few moments to work through these examples and see if you can identify which one is the acid and which one is the base in each reaction. Okay, remembering that acids give hydrogen ions and bases get hydrogen ions. All right, so pause the video, take a look, and then I'll go over it shortly. All right, so in the first one, let's see, this is water plus my dihydrogen phosphate creates hydronium and hydrogen phosphate. Yeah. Or this is, yeah. Okay, so here the water is going from H2O to H3O. So this is accepting the proton, so that's a base, which means then that this substance here must be the acid. Okay, that must be the acid. Because again, the acid gives the hydrogen, so the H2PO4 minus is giving one of its hydrogens to water to cause it to become H3O plus, and then the H2PO4 becomes HPO4. All right, and the other one, it looks like the same thing is happening. The H2PO4 is giving the HCO3 one hydrogen to become H2CO3. So here it is. This is the acid, and this is the base. Okay. Looking at the last one, same kind of situation occurs. The hydrogen from the HS minus is given to the NH3. So this is a base, and this is an acid. There we go. Right. So to recap, basically, Bronsted-Lowry acids, again, give hydrogens. Bronsted-Lowry bases get or accept hydrogens. And I guess you can easily tell in any kind of reaction, just look for which substance loses a hydrogen, which substance gains a hydrogen. All right. The assignment, well, then, to give you guys some more practice on identifying Bronsted-Lowry acids and bases is as follows. If you have any further questions, you all know how to contact me. All right, good luck and have fun.